where I am now. So I'm an assistant professor of chemistry and physics at Belhaven University, and that's in Jackson, Mississippi. So it's okay if you've never heard of it. I never heard of it until I applied for a job there anyhow. Its headquarters is in Jackson, Mississippi, but it has kind of a large footprint in the southeast. Okay, so I teach chemistry and physics there, and I really came at a very unique time, and I'll tell you more about that. Mississippi is sort of a different place when you're used to living in Iowa. So I moved from Iowa in graduate school to Mississippi. I experienced one of the top 10 winters on record in all of recorded history while in Iowa, 93 inches of snow, and the pile at the end of my driveway was so tall I couldn't throw it off of the shovel high enough to get it off the driveway anymore. So I put it out in the road and hoped that the tractor comes by and gets it. That was crazy. I moved to Mississippi in 2012 after getting the position at Belhaven there, and they had a hurricane come through. So I experienced a hurricane while there, blizzards while in Iowa, and tornadoes while here in the Texas and Kansas area and all that. I was at Wayland really as kind of a, this was 2005. I had finished high school in 2002. I went to a community college for 2 years. I got my associate's degree in Kansas. I've been dating my wife, since the end of high school, and I married her in 2005, and we came to Wayland really to finish our degree for her and for me, because we both had some credit ahead of time. So I'm kind of a transfer student, and I only spent 2 years really at Wayland, but those 2 years made all the difference really in my education. I consider the majority of things that I know and learned and implemented and used really were all done here. I even gave some very nerve-wracking talks in this very spot a few times from the different research program, different projects and whatnot I was going through. So I'm going to try to incorporate all that in to tell you the story about me, in essence. So I'm at Belhaven University now. Belhaven University was established in 1883, so it's been around a long time. Its mission is to serve, not to be served. So it's a Christian school, and it's formerly affiliated with the Presbyterian Church. So I guess they broke away from being an official Presbyterian school in the 70s or 80s, but they still hold to all of their same standards in that way. So it's a Christian university, but it's open to anyone who wants to come. We have about 4,000 students university-wide. That includes all of the branch campuses. And it's one of just 30 schools in the U.S. to be nationally accredited in all 4 of the arts: dance, music, theater, and visual arts. So not only is it a regionally accredited university, each of those individual programs are accredited by small accrediting bodies that only look at one specialty and discipline. So arts is their big thing. But I'm not really an artist at all. I'm a scientist. And so when I came to Belhaven, it was at a very strange time for Belhaven. They had built up their arts program, they put a lot of focus on arts and a lot of focus on athletics, and they wanted to sort of start switching their focus a little bit to recruit some what they call multi-talented students. Students who aren't there just for dance or just for football. And so with that switch in mind, they wanted to build up the science program, but our labs were really old, really rusty. Things were not working well. There was one guy who taught chemistry and physics, one professor who had to teach general chemistry, organic chemistry, and general physics every semester. And he did it for 20-some years, just him alone. And he ran the entire chemistry major. In addition to this one guy who did chemistry and physics, there were 3 guys in biology. I'm not sure how that works out, but pre-med's made, I don't know. And they were right on the edge. So the edge of these programs shifted. They started to want to recruit new students, but they don't have that great of facilities. Some of their professors are getting old and feeling overworked, and actually the guy who taught chemistry ended up retiring. So they hired a new guy to replace him, Dr. Reed Bishop, and he was there 1 year before I arrived. And so Reed came in, and then a biology professor retired, and then another one got cancer and left. So they're down to one new guy they just hired, and one guy who's been around for a little while, who could teach biology. And from there, they started to build their science program. Some people had doubts whether it would happen or not, but God moved. in a very, very interesting way. So you can see here on this picture on the left, there's two old buildings, and there's these weird columns in the middle. And everybody thinks, oh, those columns are just for show because they look pretty with that fountain. But these buildings used to be connected, and it formed one big like L building all the way across. I guess it was more like a U building all the way across. And the middle part burned down somewhere way back in the 1800s or early 1900s. And those columns were the only thing that survived, so they keep the columns. But the point is, these buildings are very, very old. And so one day they get a call and a visit from an engineer. And they notice that there's a crack developing in the wall. The engineer comes by and he analyzes it and says, well, I'm not sure what's going on. I need to spend some time looking at this. He schedules an emergency meeting the next day with the president. And he tells him, you have to evacuate that building. And the president says, okay, yeah, we'll look at it, we'll study it a little bit more, but the semester just started, we got to keep going. And we don't have other places to put all the people that are in that building. And he said, you have to get people out of that building, and if you don't volunteer to do it, I'll go to the authorities and we will condemn this building. And you won't have a choice. And so this started a giant crisis at the university, right? What are we going to do with all these people? This building space is going down. And it turns out in Mississippi they have really bad clay soil. And when they build old buildings on this clay, it swells and it shrinks, which leads to building foundation problems. And so this building had that problem and also had a swimming pool that was built in the basement that apparently they forgot about. So this swimming pool was built with a bunch of sand around it, like I guess the base was in sand. And they had some water leak they didn't know about that eroded all the sand away and caused the whole building to shift down and out. And so that crack was happening because the whole building was collapsing off of the front half. So that back half was collapsing. And they ended up going to the insurance company and they said, yeah, we'll give you some money, but this is a historically protected building. It has to be exactly right. And so they were able to raise money and talk to people, and what they did was they turned it into our new science facility. So they decided to actually put the money where their mouth is about building up science, right? And they gave us essentially an expanded location. We've got 3 floors dedicated to science, biology, chemistry, and multidisciplinary sciences, so physics and all that. And we get this entire building as science. I came to Belhaven right before this construction project happened, when it was kind of on the fence. And I was telling Dr. Franklin earlier, my office was at the end of a hallway, and they kind of put up a makeshift wall, said, okay, you can sit in your office over here, until we maybe find more space for you. Well, luckily they found more space in a brand new building. This has led to a 14,000% increase in the number of chemistry majors, which sounds really funny, which is why I put it on there, because we went from 1 or 2 to like 25. It was a $7 million project, and it's basically something that would have never happened had the Lord not watched out for this campus and for this university and for our science program. In essence, students have access to modern labs, modern spaces, modern equipment. Not only did they say, we want to give you a new space, they said, we want to give you new machines to do chemistry with. So we have a GCMS, a really nice one there, Shimadzu, a really great fluorimeter, so you can do all this spectroscopy experiments, nice UV vis. They're all research grade pieces of equipment. And we didn't know if we were going to get access to all these, right? We had a couple of old pieces so that we could do what we needed to do, but they said, no, we're all in and making this a great program. And so they were increased all of our instrumental holdings. So it was part of my job when I arrived to revamp physics and to re-establish and do all of the physics labs in the program. And we don't have a physics major, but physics supports so many other programs. We've built a physics minor, and we've hired new faculty. We've replaced the 2 biologists that had to leave, and we've added on another chemistry faculty member. So we have 3 in chemistry, we have 3 in biology, and we're going strong in science, trying to recruit as many students as possible. Students in Mississippi and Alabama, right? Tennessee, not Texas.
Not you guys. Y'all are happy where you are.
Sure. Anyhow, I'm going to tell you about some of the research adventures that I've been through that essentially put me in this location. That of course starts with the research I did here at Wayland. Titanium dioxide photocatalysis. And that in essence created the ramp that put me on the track that I'm in today. In graduate school, I worked on a molecule called heatin. It was an ionic liquid, and I'll tell you some fun stories about that. And of course, at Belhaven now, we have kind of a new initiative called Science and Culture. So the name of our class is Physics 125, but this is part of the general core science that all students have to take. And the goal was, the arts essentially came to us and said, look, we give you art appreciation as science majors. Give us science appreciation. We said, well, there isn't science appreciation. You need to take a biology class or a chemistry class and leave it at that. And they said, well, we're not going to. Develop one for us. Okay. So we developed this science and culture course, kind of as science appreciation, but more as science literacy. Everybody needs to know something about science. So I'm going to tell you about how that relates to also our zoo project. We've been making a lot of partnerships in the area. All right, so photocatalysis. We worked on titanium dioxide photocatalytic reactions. And I did this work with Dr. Joel Boyd while I was here at Wayland for those 2 years. And essentially it relies on the fact that we need water purification. So you'll see a common theme in all of these research projects that in some way link what you do in the lab, what you work on physically in the lab, what you learn in class, which sometimes seems disconnected, to the actual culture, the actual need around you. And those two things can work together. Right? Science is not something that has to be pursued, in the lab only by asocial people, even though there may be a lot of asocial people in science. I'll leave that up to you to decide. It's something that can impact the real world, something that can have an impact, something that you can carry through your Christian mission with. And it's just like anything else God calls people to. Use what you're trained to do, what you know to do, what your gifts are, to reach the world for Him. And science can be one of those tools. Living in Mississippi and having experience in that area with the Gulf, and essentially since all the water comes down the Mississippi Gulf there, it's filled with nutrients that plants need to live. And this has created kind of what we call a hypoxic zone in the Gulf of Mexico. Essentially that red area represents areas where all the oxygen has been removed from the water. So you have a lot of fish die off, and the shrimping industry, when the shrimp die, and this area is fished a lot and supplies a lot of the seafood for the nation. And so there's an urgent need to take care of that water, that resource, that we may be accidentally messing up in some way. So we always should also be thinking about our actions. Those things that we do as chemists generate a lot of waste and a lot of hazardous materials. So it's important to always think about it. So these nutrients, nitrates and ammonia, are nitrogen species, but it also can work for bacteria. You have really nasty water, gross bacteria, and then it can kill bacteria, and it can remove heavy metals. So titanium dioxide, which is just this white powder here, works as a photocatalyst that absorbs light and then can do reactions to clean the water. And that's what we used it for. My main focus in my research was for the nitrate removal. And Dr. Lori Pretzer, I guess she's Lori Crom now, she got married, got her PhD. I worked with her, and her job was to remove the ammonia. So we worked in tandem on this project, developing titanium dioxide into a great photocatalytic reaction or photocatalytic system. We tested at first putting it on different substrates. You could just take the stuff and mix it in with water and it would work okay. But then your water has titanium dioxide in it, which is like nanoparticles, and it's really hard to remove and filter. So you want to stick it onto the surface of something. And before we did our research, the only way you could do it was to use PVA, which is polyvinyl acetate, which is a fancy word for essentially Elmer's glue, and glue the stuff down to the surface of something, in this case, usually glass. So you glue it onto this piece of glass, and you can see only maybe 4 pieces in this picture are actually exposed to the liquid that might be running over the glass. And that means the reaction can only take place here, 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 and here. And when you zoom in, you see some of this glue actually sticks up onto these pieces. And so it's even further reduced where it can be active. So it's not so great. If you don't use glue and you just drop it on glass and let the water evaporate away, you're left with a really nice uniform surface that can do a lot of reactions, but eventually the titanium dioxide washes off. And so that's not good either, because then you have to replace your photocatalyst, you have to buy a new TiO2 to adhere it, We came up with a method using acrylic, spraying it onto the acrylic and having the acrylic get soft enough to hold the TiO2 on. And you can see little pieces of the acrylic that were liquid at one point softened up, holding on to the titanium pieces. And no one had done that before. This is actually the technology that we got the patent on while I was doing that work here. We filed for that patent in 2007, and then it was several years later it was actually granted, I think in 2010 probably. Kind of a long process. So once we developed the process and we said, yeah, I think this will work, the goal was to see, does it actually do what we want it to do? So we took this compound up here, and this compound's called methyl orange, and it just makes kind of an orange solution. And when you expose it to titanium dioxide, which has light shining on it, it can break that bond right in the middle between those two nitrogen atoms and degrade that pollutant into something that's not as bad anymore. Or that's the goal. And so you can see, if you put it on the acrylic, you get the green dots there. If you put it on PVA and you glue it down, you don't really get much activity, much degradation at all. So this is the amount of time you're exposing the light, and then you're seeing the concentration. And in the case of the slurry, which is just mixing it in with water and stirring it around, the reaction proceeds pretty quickly, and you can remove almost the majority of all of your contaminant. But with gluing it down, you barely remove any. So we were aiming for something that's kind of in between these two lines, and what we got, the green lines, happen to be the same as when you just deposit it on glass, or nearly the same. So a very usable technology. If we could develop it into a system that would be convenient to pump water through. So we also developed a reactor to pump water through. And this was part of our summer research, and that turned into fall research, which turned into spring research, and so on. Research has a way of doing that. It's a good thing overall. But we have this design with this special acrylic which will let UV light through. And all we needed to do was spray the insides of this reactor with the titanium dioxide to get it to work well. And then we just pump the water through and it will move around these channels and be exposed to the surface of the acrylic and the titanium dioxide so the reaction can happen. So we developed this reactor geometry, and then we pumped some more methyl orange through. We found we could remove almost all of it in not too much time. So this research, while I was here, only went about this far, but that was enough for me to get a patent and for us to make a couple of peer-reviewed publications on, and we were invited to write a book chapter about it. And the research continued after I left, and they found this is a viable method to actually remove bacteria, to remove heavy metals, and a few other things. Dr. Boyd was working on that even after I was gone. So down in the basement, just below us in the lab, we set up these giant floodlights for our parking lot that let out UV light. They were mercury lamps. So we put our reactor in the middle and we just pumped solution through. We took out solution and we measured how much nitrates does it have. We used the AA downstairs to find out how much metals were in the water and all that kind of stuff. So overall, we found that it can be applied to the acrylic, and it does work to remove contaminants from water. And of course, you can read about it in our paper. I will show you a picture of that. Solvent deposition of titanium dioxide on acrylic. Notice it comes from Wayland. So we published it while we were here. It was good stuff. I think this is one of the main reasons that I got accepted to all the graduate schools I applied to. I showed essentially, in some way, that I could go through research. And that's what graduate schools want to know. Are you going to be successful doing what you're doing, what you will do in graduate school? Okay, we also published in the Journal of Photochemistry, Photobiology, the effect of platinum oxidation state and concentration on the photocatalytic removal of ammonia with platinum-modified titanium. So that was Lori, myself, and Dr. Boyd working on that. Here's a picture of the patent. And notice it wasn't granted until I moved off to graduate school. It's a long process. Almost in 2011. And then, of course, a book chapter. So you can find it on Amazon. No, I don't recommend it. You pay $300. It's in high demand, right? That's got to be it. There's just one copy left over. No. All right, from there, I went to graduate school. I applied to a number of places. I got accepted in all of them. I ended up going to Iowa State University. And while I was at Iowa State University, I took the great experience that I had here at Wayland, and I took the knowledge that I learned in classes and that I had applied in undergraduate research and developed it kind of in a new way. I had an amazing foundation. You know, I wasn't sure going to graduate school that I would be as prepared as everyone else. And I was more than prepared, even more than other students who entered graduate school the same year I did. I was ready to go in classes, I was ready to go in research. I had already experienced the life of almost full-time research, summer, fall, spring, and so on. And because of that, the transition to, okay, well, welcome to graduate school, we're going to slowly get you started into research. I experienced this kind of slow time that Dr. Franklin was talking about earlier. It's because I was already revved up to the highest level, I guess. One of the projects I got to work on was ionic liquids. Ionic liquids are a very unique type of material because they're ionic compounds that are liquid at room temperature. Okay, so ionic materials are usually things like crystalline solids, salt, table salt, NaCl. That's an ionic compound, right? And to get it to be a liquid, you got to heat it up to like 1500 degrees or more. Those ionic bonds are very strong to get it into the liquid phase. But these ionic compounds are liquids at room temperature. And so that means they're considered to be very friendly green compounds. They don't evaporate. If you're using them in some industrial process, they're not going to be very volatile and create hazardous environments. They're not going to destroy the atmosphere. This is the thought when they were first discovered. And so essentially you have this anion and cation together, and they're sort of complex materials, but they are new and interesting because you can customize their behavior by changing the different functional groups that you put on the molecules. So if you want something that's more viscous or less viscous, you add a side chain or remove one. All these different properties, you can sort of customize the liquid that you need that's considered environmentally friendly for your particular application and process. And it's found that they perform as well as commonly used solids. So if that's true, we're potentially standing on the edge of being able to replace all these hazardous materials that are being used with ones that are considered to be more friendly, as long as they're not getting contaminated and we're having to buy a bunch of them to replace all the ones that we're using up. And while I was doing this work, Iowa State University houses the Department of Energy Ames Laboratory as part of Iowa State's campus. So I was working with a major professor who had a contract in both places. So he was interested in Department of Energy projects. He was is a computational chemist. And he was interested in regular academic projects together. And so the Air Force essentially came to him and said, we've heard about these ionic liquids. They're going to be great replacements for all the hazardous materials that we're using, we think. But they need to meet some criteria for us. They need to have high energy density, which means when you burn them, you get a lot of energy out, even though they don't take up very much space. They need to be very thermally stable so that we don't have to, worry about them exploding in a storage facility or under harsh conditions in the field where they might be. They need to have a low handling hazard. They shouldn't be sensitive to impact, to friction, to discharge, electrostatic discharge. They should have a very low toxicity. We don't want our guys having to get in hazmat suits to fill up the jet or the rocket anymore if we can use these as fuels. They can be produced simply, and of course they desire, this is their category of things they want, low costs, 3 or less synthesis steps. It's like if you were to dream up all the things you could possibly want in one thing, this is that list. And so maybe it's not super achievable. However, they wanted us to do some experiments on these liquids. They didn't know how fast these liquids would actually decompose in a combustion reaction. And so they needed to know, what is the time limit? Are they so viscous, or do they have such properties that they take too long to use as a fuel? Or can they be combusted very quickly with a high energy output? And so they came to us to figure that out. Now, I said my boss is a computational chemist, which means he's doing ab initio electronic structure calculations to figure out how molecules are put together. And he's interested in more theoretical things. And so they wanted some theoretical things in addition to wanting some experimental things. And so normally when you go to graduate school, you have to make a choice. If you're going to study physical chemistry, do you want computational chemistry or do you want experimental chemistry? experimental physical chemistry. Basically, do you want to work with lasers and spectrophotometers, or do you want to work with computers and software? And I had chose to work with experimental physical chemistry. When I got to Iowa State, I developed a really great relationship with one of the professors there, Dr. Stauffer. And I selected him as my major professor, and I got accepted into his group. And after they let me into his group, a few months past the next semester, they went to him and said, "We're not going to give you tenure. You need." So they essentially removed him from the university, and I had just joined his group. So this was a huge problem. If you don't have a major professor, you don't have someone to work with, you don't have research that you can do. So they just told me, "Oh, we'll just join a different group." But they had all just selected and filled all of the positions that they had funding for with all the other new students. So here I was, sort of at a crisis, and I went to talk to the lady who handled all the new graduate students. And I said, "Here's my situation." She said, "Yeah, I know, I'm sorry. They should have told you something ahead of time, but they didn't want to let him know that he wasn't getting tenure until they knew he wasn't getting it. And so it's kind of unfair for you. If you need to, I think Target is hiring." Thanks. Where do I go from there? Well, I had relationships with a few other professors, and so I went to talk with them. One of them is Dr. Teresa Windus, who is a computational chemist, also a very strong Christian at Iowa State University. And I talked to her, and she said, "Well, you can join my group if you want, if that's the research you're interested in. But what I would recommend is, since nobody really has a spot to take on a full student, some people might have enough money to take on half of a student." And I was like, "But I'm not a half of a student." She said, "You join multiple groups. Then you'll get experience in multiple places, and it can work out really well for you." So I ended up joining Dr. Jake Patrich's group, which is experimental physical chemistry, working with lasers, and joining Dr. Mark Gordon's group, which does mean that I had to write papers that were edited by both, and they were correcting each other's corrections. However that would work out, right? But it turned out to be a really great experience, something I didn't expect. I didn't have to leave graduate school, and it worked out better than it could have. As a matter of fact, one of the things about having two major professors is when you get fed up with one or the work that's happening in one place, you just go and work in the other one's lab. So you can go back and forth. But in reality, it kind of meant that I didn't belong to either group. So does that make me an outsider in some way? Well, not really. It put me in an interesting situation where they said, "I don't want to use all my money to pay for you to do research for me, but I can use half of it." And then when they would both agree, then I would be on a research assistantship and get paid a stipend to do research. When they wouldn't agree on which semester it would be, I would teach. And the department would pay me to be a TA, which was standard for all graduate students at Iowa State. So you start out your first couple of years, you're teaching anyway. And for me, it turned out to be more than 2 years of teaching, 3 years of teaching, 4 years of teaching. I taught 7 semesters of general chemistry, which was more than anybody could remember any graduate student ever teaching. And I thought, I'm wasting all my time teaching when I need to be doing research. But it was because of my teaching experience that it was such a smooth transition to an actual teaching job. I think that's one of the reasons that I was able to find a job at Belhaven so easily, because they said this guy already knows how to teach, already has great student evaluations, will be a great part of our team. So something that I thought at the time was not that great turned out to be something that was a huge blessing for me. And I got to work on experimental and computational chemistry. So it really turned out really great overall, had many great benefits. So for this project, we wanted to approach it both computationally, doing calculations on the computer, and experimentally with lasers. So here's what the Heaton ionic liquid looks like. And it's relatively unstudied computationally, which made it a great project. There's barely any information about it out there, and it has a lot of value, potentially, to the Air Force. So we wanted to calculate its structure. No one had even done that. So the group I was part of used a software called Games. So it's kind of funny now, because I can tell people when they ask what do you do for research, I say, I run games on the computer. And all he does is play games on his computer. It stands for General Atomic Molecular Electronic Structure Systems. Games. And so it allows you to calculate at high levels what we call ab initio, which is from the beginning calculations, treating each electron and its wave function separately and putting together that calculation to find the lowest energy state of a particular molecule. How does it normally like to behave or structure itself? Okay, so we were able to use games to assess this ketone molecule. So at first we just start with one cation and one anion. And we calculate the structure, and you can find how much energy they all have compared to each other. The highest energy state and the lowest energy state. And the reason this is valuable is because it tells you how the molecule normally likes to be at the lowest energy state. One thing you can almost always count on in science is that things like to be at their lowest energy state. Just like students. On the couch. And in order to go to a higher state, you got to get energy, right? You got to eat the chili dog to get up off the couch. And when you do have more energy, you can move to these other shapes and these other configurations. And so the lowest energy state, the one down here on the bottom, shows really good separation of charges, as they all pretty much do, but also shows that the two sides of the molecule, this piece here and this group here, hydroxyethyl group, holds that nitrate in. It kind of corrals it in like it's going to give it a big bear hug, which is important to thinking about the structure of these molecules, because we wanted more than just one cation anion, we wanted two, which we call tetramers, because there's 4 molecules there. And so we also calculated all the structures for the tetramers, and we found this one to be the lowest energy state. So it's interesting that it's not 2 systems that are sort of hugging the nitrate there. Instead, they're avoiding each other, but the part of the anion that can associate with the other molecule is in some way in the lowest energy state. Okay, so it's almost making this regular pattern that you see with normal ionic compounds. The positive, the negative one, the positive one, the negative one, repeating. And even in the higher energy structures, you can see they start to go back to one another, which you can tell is not something that they would normally want to do, actually quite a bit higher in energy. So they prefer to look like this. Now once you know this information, you know a lot about the molecule as far as you can calculate its thermodynamics, how fast it might actually degrade if you were to expose it to a reaction. And you could know about its hydrogen bonding linkage, which was important to assess as well. Now the question is, if this is just theoretical, how does it actually behave experimentally? So they had to send us a sample. Okay, so they told me, we're sending you a sample, it's going to come in on this day, expect it. So I get a call to the mail room, I go down, and they shipped me a barrel, right? A giant metal barrel. And I'm like, oh man, I don't need that much. This seems pretty hazardous. So I open the barrel up, and inside the barrel is a bunch of bubble wrap. Okay, I get the bubble wrap out, and in the middle is a paint can. And I get the big paint can out and open it up, and there's a lead pipe with lead ends screwed on it. And I'm like, okay. And I take the lead pipe off, and in the middle of that is like a Kevlar absorbent material. In case it exploded, they didn't want any shrapnel, I guess, and it could absorb up. And I lift that up, and there's a small paint can. And I open that paint can, and then there's a little vial, and in the vial is a little bit of liquid. They sent me 3 milliliters. And I had to take these 3 milliliters and stick them in front of a high-powered laser to do my experiment. So I'm wondering, is there going to be an explosion in the lab? Because some of these ionic liquids are not stable if you expose them to acids and other things. Or what if you expose them to a really high-powered laser? Well, I still have all my fingers in it. There was no explosion. But what we did was we took that liquid and we added a dye to it, a fluorescent dye called Coumarin 153, or just C153. The good thing about this dye is it lets you see its fluorescent spectrum really well. And so we wanted to analyze, we had an instrument called a time-correlated single photon counting laser. And we used that laser to send in 1 photon at a time and watch 1 photon come out. Now, you probably remember a photon is 1 particle of light. So we sent in 1 particle of light at a time and watched 1 particle of light at a time come out. So this was like 6 months sitting in a super dark room with the computer monitor turned down as low as possible, hoping that no one walked in and messed up my experiment by letting some light into the room. You're counting 1 photon, so if you get a stray photon, it's really going to mess you up. However, we were able to make it work, right? And so we constructed what's called the time-resolved emission spectrum. So our high-power laser operated on the femto and picosecond scale, and we were able to get resolution in the nanoseconds here. So you can see steady-state spectra, the ones labeled SS there, is the one that you would get off of an actual fluorimeter. If you just went to the machine and you took the fluorescence spectra, you would get the steady state spectra. But in reality, what happens is those fluorophores shift to that steady state. They start at some t equals 0, 0 time, and they shift from there to the steady state position. And you just have to have a machine that's fast enough to measure that. So notice after about 5.05 nanoseconds, it was already shifted to the steady state, in essence. So from this information, you know how fast could it possibly actually move as a liquid. How fast can this solvation process happen? Can these molecules rearrange? And from that, we can figure out how long it would take for them to combust or to undergo reactions. Because reactions involve those molecules moving. And so we constructed the solvation correlation function, which lets us compare how the liquids at different temperatures could actually rearrange. How fast can it actually happen? So notice 50% of the molecules have already rearranged in a very, very short time period. And at room temperature, it takes them a little bit longer, but if you heat them up, it happens really fast, which is exactly what you would expect. A warm liquid, those molecules can move faster. Remember, thermal energy requires or allows molecules to do a lot more movement. So depending on what temperature they're doing their combustion at, you can rest assured that the combustion will happen fast enough if a few nanoseconds is all it takes for it to rearrange. So the fact that it can actually rearrange means the combustion can happen on a fast enough time scale, and there wouldn't be an issue with using it as a fuel. So overall, it is a good fuel, or could be used as a good fuel, because it meets the majority of criteria that they want. Now, I don't think that means that they're going to go and just buy a whole bunch and convert over to that. But they're constantly thinking about what alternatives do they have. Because they told us sometimes we'll have rockets up in the air and they'll stop functioning and they need to be brought down. How do we do that? Usually we shoot them out of the air, which means we have all this hazardous rocket fuel coming down, raining over the planet. And we don't want that because it's not good for the environment, it's not good for the communities, and so on. So on average, solvation can happen in 0.62 nanoseconds, and the molecules can rotate in 21 nanoseconds, so fast enough for the combustion to happen. Now, I want to tell you a little bit about some of the new work that we've been doing at Belhaven in our science and culture class. Okay. I already told you that they wanted science appreciation because they already had art appreciation. That's what they were demanding. So we had to develop this new vision. And the vision here was that we could expose students to the wonder of creation and hopefully get them thinking, have a little bit of curiosity about the natural world. We could maybe use large current events to motivate discussion of content to deliver physics and chemistry information to students who were not scientifically inclined or who are not. So we have several goals we want to accomplish, including content, and this happens mostly through a lot of the partnerships that we've been able to make, particularly the Jackson Zoo. It's the first main project that we've done. And so we took this approach, which is referred to in education as the SENSOR approach, which stands for Science Education for New Civic Engagements and Responsibilities. This is sponsored in part by the National Science Foundation. And so SENSOR model just seeks to engage students in cultural ideas and things and use those cultural things to give them content, to expose them to science. So that was our goal. And we're going to use those current events to motivate content as well. So these are things like Mars orbiter, eutrophication in the Gulf of Mexico, renewable resources, reusable energy, and of course, being in Mississippi, the Mississippi River, and anything that the zoo wanted to do. Several challenges with this. There's not a textbook. There's not an easy way to do it. So when the zoo came to us seeking a partnership, it was really great. They're creating a master plan, and they said, we need data for our master plan. Who uses, what exhibits, how many people, we don't track anything. We need help. Which is kind of strange, I thought, for a zoo. They didn't even know where their water was going, but they got this like $125,000 water bill from the city. And they said, we don't use water like that, but we don't monitor the water that we use. So what's going on? Well, through our research, we were able to build heat maps of the area. We tested the water in all the different exhibits. We went through and found out where the water was going, where people are, and just provided a lot of data for them to craft their master plan. That was the main goal. our heat mapping study found that the warmest areas, and I know that's hard to read because this is all the exhibits at the zoo, the warmest areas were the playgrounds. Those top 3 are playgrounds that they have for the children at the zoo. Oh, go play in the playground. It's 100 and, yeah, too hot. And the black bear exhibit was really hot. Giraffe exhibit was really hot. And this is stuff they had never thought about, really, the habitat of where their animals were. And you can see kind of red corresponds to really warm regions. We used our computer science colleague to help us generate this map. We also mapped it through GPS and figured out elevation and all that other stuff. So we were able to expose students to GPS information, which includes information about basic physics and positioning, thermal studies. We talked about what thermal energy is, what temperature is, water studies, what are different nutrients, how does water work and behave, air quality, and our biology faculty members did an invasive plant study at the zoo. So this partnership opened up a really great avenue to expose students in new ways and to help out the zoo a little bit, who is really struggling. We got a lot of media coverage from that. And we have plans to go to the Pearl River, which is in the middle of Jackson, and do some more studies. But I want to bring you to some overall arching conclusions. All these projects in some way are using science to benefit fellow man, right? And so chemistry really can be used to love your neighbor. Jesus told us to love your neighbor, right? First, love God with all your heart, all your soul, and all your mind. Then love your neighbor as yourself. If you're trashing up your neighbor's backyard, if you're exposing him to hazardous materials, even if you're not doing it on purpose, you should try to rethink how you're doing things. And you can use science to do that. Chemistry allows you to be a servant to others and really love God with all your mind and your neighbor really to its fullest. Of course, this work wouldn't be possible without a lot of people. So here's an acknowledgement slide, but there's a lot of people who are left out. And thank you for listening.
We can take just a couple minutes if you'd like to ask any questions. Let's open up the floor to some questions.
For a student interested in possibly going to graduate school, what do they pay you to do that? Is it like a job?
Yeah, that's the way I approached it. So I was married already going in, and so I had to provide for my family, right? And so the question is, how do you do that? Well, I decided to treat it as a job, right? When they accept you to graduate school, at least in the sciences, they'll write you an offer letter which includes your stipend. At Iowa State, you got paid your stipend for doing teaching for them. So that was part of the deal, but not all graduate schools require you to teach in that way. But that's a big push at Iowa State. Also, research. So they essentially said you're guaranteed X amount of dollars for 5 years. After 5 years, you have to start petitioning for it because they don't want people to be in grad school that long. But
So just to get things straight, they pay you to go to graduate school?
they pay you to go to graduate school, yeah. And probably more than you would make doing some other things in a lot of cases. Maybe not entering the workforce directly, but it was enough with the fact they gave you tuition waivers, you don't have to pay any tuition. You only had to pay a few $100s in fees, but they gave you insurance. They didn't give any insurance to my wife, which was a little bit distressing at times, but we were able to work that out. And I approached graduate school as a job from that perspective. Okay, if you're thinking about it as school all the time, oh, more school, I got school, it's school, I got tests, it kind of is a drag. But I thought of it as, oh, I need to go to work, I have to earn this money, I need to support my family. I'm going to think of it as a job, and that'll allow me to disconnect a little bit, I think, psychologically, so it's not too overwhelming. Because a lot of graduate school is about psychological hardiness. Right? Dr. Boyd used to say in a lot of ways it's an endurance degree. Can you make it through all the stuff they're going to throw at you? And so disconnecting it as a job for me really helped a lot. That way I didn't take it personal, it's about your performance at work. Yes?
Would you recommend that the students at Wayland get engaged in research as soon as they could?
Yes. Yes, I would. The more research you have under your belt, the better off you will be as a candidate for graduate school, or really for future jobs. It sort of depends on what you're targeting. When I came to Wayland, I just wanted to get my degree so I could go and get a job. But my research experience really opened up a giant area for me that I had never considered and never thought about, and that was doing research as a living, or at least while you're in graduate school, or going to graduate school. I just wanted a job so that I could get my paycheck, so that I could support my family. And it turned into go to graduate school, learn more about God's world and science, and then you use that in a new and different way, something I never would have expected.
Thank you.
Yeah.
How'd you hear about Bellhaven when you were in Iowa?
So at the end of my time at Iowa State, I was applying for jobs everywhere. I wanted an industrial job. Work in industry, hopefully make big bucks, right? But I wanted to work for a company and be a valued member of that company. So I applied to a ton of companies and got a really great hit on a mining company. They wanted somebody with high energy molecules as a background. But that didn't work out. And nothing else worked out after that. And so I said, well, I'll apply to some schools. So I went to what's called the CCCU, Council of Christian Colleges and Universities, and looked for any openings that they had. And Bellhaven had an opening on the CCCU website for a chemistry professor. So that's how I applied. I applied at several others as well. Got a really great offer at Fort Hays State University in Kansas, and this offer from Bellhaven. But I had never heard of Bellhaven before at that time. And that's what ended up working out a lot better than the other offer that I had.
All right, let's give one more round of applause. I think he earned the Association of Former Students and Danny Andrews would like you to have this Wayland blanket so you can take back and have that, hanging on your wall. Bellhaven, that's fantastic. Thanks for using it. Appreciate it. Thank you for being here. You guys are all invited to come next door to our reception. So we have cookies and fruit and stuff. So come have a chance to visit a little bit more informally with Dr. Carlson, find out a little bit more about his experiences. And if you have any additional questions, you can ask him. But please join us next door. And with that, you guys are dismissed.